All right, where did I put that? Good grief. I can't find anything in here. I don't know. Oh, crap. This is the first in the series of 3 videos where we're going to explore how a computer performs the addition of numbers. We're going to start at about a 30,000 foot level, and gradually we'll come in and look at the details of how that might be implemented in circuitry. Let's get started on this. Okay, let's just kind of quickly go through the setup here. Here we have 2 numbers, the number 13 and the number 11. The number 13 is 1101 when we set it up in binary. The number 11 is 1011 when we set it up in binary. We have 13 as our top row and 11 as our second row. And we add in much the same way as we do when we're adding numbers base 10. It's just there are fewer addition facts to remember. We just go 1 plus 1 is 2. 2 is represented with a 1 and a 0, so I put down a 0 and I carry the 1, and then I have 1 plus 1, again that's 2, put down the 0, carry the 1, 1 plus 1 is 2, okay, put down the 0 and carry the 1. Now I have 1 plus 1, that's 2, so I carry a 1, and so I take then 0 plus 1 is 1, and so I had the 1 that I carried before. 1 plus 0 is equal to 1. And if we dig this out, this is 0 times 1 plus 0 times 2 plus 0 times 4 plus 1 times 8 plus 1 times 16. That's 24, which is exactly 13 plus 11. What I want you to notice here is that we start over here on the right-hand side and we proceed toward the left, one column at a time. Okay, so remember that as we go on to the next step. What you might have noticed when we were doing our binary addition is that the case in the first 2 bits that we're adding together is different because there's not a carry in. On that, you just combine the 2 digits and you put down either a 0 or a 1 as appropriate. And then you will carry out to the next. So here we have it set up. B denotes one of my binary digits, one of my bits, and B2 denotes the other of my bits. And I have all 4 different ways that this can be set up here on the left-hand side. And then on the right-hand side, I get the product of this. Okay. Now, so again, when we're carrying out our binary addition, we can think of it as being carried out in time, as it is. And we start out on the right-hand side and proceed to the left as we're doing our operation on paper. Okay. Now, when we diagram this, okay, we can think about this, and this is the metaphorical black box. Yes, I know it's white, but the metaphorical black box where we put in bit 1 and bit 2, they go into this box, which we don't have any description of what's happening there. You just follow the arrows in, and there's an output. Okay, the one output is what we write down in this operation, and the other output is what we carry out to the next operation. And now here, even though when I carry it out on paper, I go from right to left, when I diagram it out, I am going from left to right and following the directions of the arrows. Okay, and so this is called a half adder, and it does more than just that first digit. So we'll see in the next part of the video. When we come to the second column in our addition, we have to, and all subsequent columns, we have to account for what's carried in from the previous operation. And so when in this full adder table, I've put in an extra column before the B1 and the B2. So here I'm dealing with 3 bits rather than just 2 bits, and so I will have 8 possibilities that I have to account for other than just the 4 possibilities. Now, if you make a comparison to this top half of the table to the half adder, you'll notice that since I have zeros that I'm carrying in, it's exactly a half adder. Okay. The second part of it looks different because I'm having to account for that digit that I'm carrying in. But again, what the device does, it takes in these numbers, okay, and it takes in 3 bits and it spits out 2 bits, the sum that we write down and the carry out that we carry to the next operation in the next column. And this is represented in this black box where we have the 3 inputs, the carry in and then my 2 bits. And it'll also carry out, okay, and wrap around here to put down the sum of the 2 digits. And so this is a black box, and I'm hoping, in this video, before I end, I'll have a slightly better idea of what goes on in this black box. I want to do an example on the same addition, kind of showing you the mechanics in perhaps a way that'll reveal more. We start with our 1 plus 1. What are we going to do there? We're going to, again, combine these together in a half adder. Okay. And the half adder, 1 plus 1 is 2. We spit out, in binary, that's 1 and 0. So we carry the 1. And we put down the 0. So now we go to the next level. I have my carry of 1. Carry of 1. I have my 0 there, and then I have my 1. Okay, now I combine my my carry in and the 0 of that top bit. I combine them in a half adder, and this will give me a 1, okay, and I'll be carrying a 0. All right, now I've got this 1 that I got by combining my 1 and my 0. I combine it with the 1 from the second spot. Okay. Again, this should be a bigger box. Combine it in this half adder box here. Okay. And so 1 plus 1, well, that's 2, so it's 1, 0. And so I take and I put down my 0 here, I have this 1 and this 0 that I'll then, I add them together, as it were, combine them in some way. And when I do my carry out, okay, my carry out will be a 1. And I could just do another half-hour adder there, but that's just too much overkill. I'm going to show you my solution in the next piece of this video for combining my carry out here and my carry out here to get the final carry out. Okay, so this is a table for logical OR doing 2 bits here, B1 and B2, and this is read, this third column is read B1 or B2. And 0 or 0 is 0. Or you could read it false or false is false, false or true is true. Read it either in codings, and it's fine. But this is a logical OR. And this is represented in diagrams by what's called an OR gate. And we'll be learning more about logic gates in subsequent videos. This is a representation of an OR gate. The idea is that you have 1 bit coming in on the top, a second bit coming in on the bottom, and when you combine these 2 bits in OR, it comes out on this end. And so it's all kind of arrow-shaped anyway, and that gives you a direction of its flow in time. Okay, so this diagram is a first stage attempt to take the blackness out of the black box of the full adder. What we see here, we have our inputs with a carry in, bit 1, bit 2, and then the digit we put down. We put our carry in into a half adder along with one of our bits. Okay, it'll spit out a digit here that we'll put into another half adder to combine with our other initial bit, but it'll also have a carry forward that we'll send to an OR gate. This second half adder, it combines again the sum from the first half adder with our second bit. It'll have a carry that it goes to the next OR gate. It'll be an input to this OR gate as well, and then but its final output is our final sum we put here. And so this OR gate, it's really just a little bit of overkill because it'll never have to handle where we are carrying ones at the same time, because one of these will always be a 0 in this particular case. Okay, but it will help us to combine the 2 outputs of our half adders to get an accurate carry forward to the next stage. And so what I hope to do in subsequent videos is to kind of fill in the black box of what happens in a half adder. Yeah, who is it? No, I'm not doing anything. Come on in.